Good morning, everybody, and welcome to Statistics. My name is Fred Strail. You can call me Fred, or some students call me Dr. Strail or Professor Strail, or whatever. I've been doing this quite a long time. I've actually been a statistics professor since 1998. I've been at Indian River State College since 2004. Teaching this particular class, Introductory to Statistics. I took a 2-year break, however, and I went back to Detroit, which is my hometown, for a couple, excuse me, that does it all the time. For 2 years, I was an assistant professor at Wayne State University in Detroit, teaching in the medical school, biostatistics to medical residents and interns. Before that, I was teaching in the grad school at University of Michigan, pretty much the same course to graduate students. And then before that, I was at Wayne State University. I got my PhD in 2000. Before that, I was a teaching assistant with my statistics professors. And then before that, I was a statistics tutor as an undergraduate and part of the beginning of graduate school. So I've had a lot of experience teaching this course, tutoring this course. I was a student back in 1995 in an intro stat course. So I have lots of experience teaching and also working with different issues that students have with an intro stat course. Now we have rules. This course is not easy. We have rules, and the first rule is you have to study. This is so important. This is not a class that you take lightly. There's a lot of new information in this course, and it takes repetitive study. Statistics is a branch of mathematics, but it's actually a language. You're going to notice that the actual math that we do in this class is pretty easy. The math in this course is not the challenge. Okay, now if you remember, the prereq for this course is introductory algebra, intermediate algebra. We don't really even do algebra in this class. Okay, statistics involves a lot of concepts. It's actually a language. This class is hard and requires a lot of memorization. So you have to, study regularly. Please come to class on time. Typically, like I said, I've been doing this for a lot of years. Typically, students who are chronically late don't do real well on exams. So, I will cover a certain, amount of material, and the student walks in 5-10 minutes late, you miss that. Also, it kind of disturbs the class a little bit, so just try to make it to class on time. And also don't miss class unless absolutely necessary. Now there are, so we're going to say attendance is mandatory. Now there's a lot of legitimate reasons for missing class. I had to take my daughter to the hospital, family issues. But if you're just going to blow off class, it's not a good idea. And if you do that, you get on my bad side. Okay, so attendance is mandatory. Now we have a textbook for this class. It's Introductory Statistics by Prem Mann. Now the latest edition is this 8th edition. It's got a baseball bat and a baseball on the cover of it. But I actually sent the class an email before the semester, a few weeks before the semester, suggesting that you go online and purchase the 6th edition used. The 6th edition. It's got a bunch of tropical fish on the cover. And you can actually get it for about $10. I think a student told me the other day that she got it for $10 including shipping. So it's 10 bucks out the door versus about $90 for this thing. Okay. Textbook authors, they come out with latest editions to make money. Okay, so you know, most of the material that's contained in this is also in the 6th edition. I would much rather you guys save a few dollars, get the 6th edition. Okay, it's pretty inexpensive. Now, as with any textbook, there's a lot of information in these textbooks. Look at your accounting textbook, your intro biology text, your intro psych text. They contain lots of information. Now, you know, like 5 semesters worth of information in a single text. It's my job as your instructor to extract what I feel is the most important information, you know, out of this textbook and teach it to you. But I also teach you, you know, information that's out of other textbooks. So some of what I teach you will indeed be in our textbook, but some of what I teach you will be, you know, out of other textbooks and other, you know, sources. Okay? The reality is, you know, we don't really need textbooks anymore. We have so much information online, but, you know, for this class we'll be, you know, using this text. Also bring your calculators to class. You don't need a sophisticated calculator. A simple 4-function calculator that you could buy for $5 at Walmart will do. So you don't need anything as sophisticated as a TI-83 or anything like that. Now the thing about this course that you have to be careful about, statistics is easy at first, as you will see in these first couple of introductory lectures. We're going to be introducing basic concepts, and you're going to, you know, sit and you're going to say to yourself, well, this is, you know, pretty easy stuff. But we're going to be doing some simple computations, going over simple concepts. Okay, this course starts out easy, and then it gets more challenging. So don't get cocky. Just be humble, be good students. And another thing is that the math is easy. You're going to notice immediately that, you know, the actual computations we do are pretty, you know, they're arithmetic. They're actually pretty easy. The real challenge in this course is assimilating this new language into our heads. So, you know, this course requires a lot of memorization. It's kind of like taking a bio course and learning about the cell, or taking a French course and learning the conjugation of verbs and stuff like that. There's a lot of statistical concepts that we have to, you know, assimilate and get under our belts here. My job as your instructor is to prepare you for our exams. Contact me anytime, okay? Probably the best way is to call me on my phone. This is actually my cell phone. I'm from Detroit, so this is my Detroit area code, okay? Also, email me at this irsc.edu email address, or you can contact me on Angel. Please check Angel every day. I post things, I provide study guides, review sheets, a lot of helpful information that I post on Angel. I'll also check the box, and you will get that same email on your webmail account. Okay, but good idea to check Angel every day. Now, I do meet with students periodically for tutoring in the library. Remember, I started out in this business as a stat tutor, and I still tutor to this day. But lately, over the past few semesters, we've been conducting tutoring sessions over the telephone. You know, telephone tutoring. Now you have to remember, tutoring is not re-lecturing. If you want to re-lecture, you look at this video again. Okay, tutoring is not re-lecturing. Tutoring is designed to help answer questions. Tutoring is answering questions. So come to a tutoring session with 6 or 7 questions, okay? Or call me on the telephone. Dr. Strahl, I have a question on this, and this. I'll be glad to answer it for you, help you. And if I don't pick up, just leave me a voicemail. I'll get right back to you, okay? And also, contact me if you're going to miss a class session. And if you just arbitrarily decide to blow off class for whatever reason, not a good idea. That's the easy way to get on my bad side. All right, you want to, you know, if they have a legitimate reason, you know, just, you know, contact me. But be in class, very important. Exams. About 1/3 to 1/2 of this course is actually descriptive statistics. Now these first couple lectures are going to be introductory in nature, so we're not going to actually get into descriptive stat per se until sometime next week. But about a third to a half of the course is descriptive statistics, and about a half to 2/3 of this class is inferential statistics. Two different things. This builds on what we learn in descriptive stat. We'll have 4 exams, equally weighted, each worth 25% of the final grade. Multiple choice, true and false. Now, taking multiple choice tests, your job is to recognize the correct answer. And typically, students who are studying, are putting forth the required effort, have enough knowledge to get 7 out of 10, 8 out of 10 questions correct, 9 out of 10, that's C, B, or A. You should have enough expertise. I don't expect you to be experts, by no means, but I do expect you to be able to recognize the correct answer at least 7 or 8, out of 10 times. And that's a C or a B, or 9 out of 10 times, which is an A, okay? And again, it's my job as your professor to prepare you for the exams. And I do my darndest to do that. For this first exam, which is coming up in a few weeks, I provide you with a lot of study guides, study aids. I even write you a letter that's pretty much verbatim, out of my lecture text. And it's a really good idea to take good notes. Typically students who are getting A's and B's have really impeccable notebooks. Students who are not doing too well, disorganized, a lot of chicken scratch in there. So it's one of the characteristics of good college students is that good college students take good notes. Very necessary in this class. So this is where our lecture begins. Statistics is indeed a branch of mathematics, but it's really a language, and we call it the language of science. Now, you guys are familiar with the sciences, the natural and physical sciences, biology, chemistry, physics, the behavioral sciences, psychology, sociology, anthropology, environmental science, political science, science. One day I got the dictionary out. I just had some time on my hands, and I looked up the word science. The definition was about this long. One of those definitions, it's an approach to gathering knowledge. Science is an approach to gathering knowledge. Statistics is a big piece of that. Now, if we remember, science has 2 primary functions. The development of theory. We know what theories are. They're sets of relationships thought to explain outcomes, so to speak. And the testing of hypotheses. We know hypotheses are statements. A hypothesis is a statement. So, in a real general sense, we have a method. We have a method to this approach to gathering knowledge. And we call this method the scientific method. And we've all heard of this. But let's take a look at this scientific method a little bit more detail. If you open up any quantitative scientific research article in the scientific literature, the Journal of Nursing or the Journal of Business, the Journal of Experimental Psychology, the Journal of Political Science, and underneath that abstract, you have your title, and then underneath the abstract, which is a little summary, and then that very first paragraph of the article is called the problem statement. Now, it doesn't specifically say that, but that's what it is. Identification of the problem. Scientists are in the business of solving problems. Problems everywhere. Problems in medicine, problems in agriculture, problems in nursing, problems in, scientists are in the business of solving problems. Well, probably wondering, how do they do that? They formulate hypotheses. And these hypotheses are thought of as solutions to the problem. These hypotheses come in a couple of different forms. These statements come in a couple of different forms. One of which is a statement about relationships between variables. or differences between group means. If you don't understand that, that's fine. We're going to be talking about that a lot down the road. But right now, I just want to emphasize that this class, this introductory statistics class, is really about collection, organization, and analysis of data. You see this term analyses is pluralized. Data analyses, there are many different types of data analyses, but the term data analysis is synonymous with statistics. So in any scientific research article, you're going to see a section called data analysis. And that data analysis is the statistics and the formulation of conclusions. So really, what this class is about is this piece: collection, organization, and analysis of data. That's what this class is about. So then, statistics is a set of procedures for measuring things. We're going to talk about measurement in the next class session. Biopsychosocial phenomena, I just threw that word in there. That's kind of an all-inclusive word. Collecting data. Those data are just simply sets of numbers. These numbers represent something. So I could measure your heights. Let's suppose that I decided I was interested in the heights of all IRSC students. I'm interested in the heights of all 37,568 IRSC students. But you know what? To make things a little bit easier for me, I'm just going to measure all 38 of your heights. So let's pretend I do that. So I measure your heights, and I have them all listed. You know, student number 1 is 78 inches tall, student number 2 is 63 inches tall, student number 3 is 73 inches tall, and so on and so forth. I have 38 height measurements. I have essentially collected data. These data, these numbers represent your height. I could compute an average height. I could sum the scores and divide by 38. Okay? Organizing, summarizing, and describing data. That's called descriptive statistics. We have a whole section on that. Okay? There's actually 5 descriptive statistics. We're going to be starting in on that section next week. Okay? Making decisions or inferences from those data. That's inferential statistics. Okay? Is what I'm seeing in our sample of 38 in terms of height, let's say, also going on in the population, in all IRSC students? In other words, I determined the average height of our 38 students to be 5'6" tall. I automatically conclude that the average height of all IRSC students, that's the population, is also 5'6" tall. I use inferential decision to make that determination. Now you might be thinking, Dr. Strail, come on. There's 38 people here. Yeah, the average height is 5'6", but gosh, there's 37,000 plus IRSC students. The average height might not be 5'6" tall, and you know what? You're absolutely correct. You're absolutely correct. But, you know, again, describing data and making an inference, generalizing from sample to population. We'll talk about that actually in a few minutes. Let's back up a little bit, class, and talk about the basics. Let's just talk about the basics. You know, and again, this is introductory stuff. We're not doing any statistics these first couple class sessions. We're just sort of introducing, you know, terms we're going to be using the rest of the semester. Data we know to be sets of numbers. These numbers represent some form of measurement. Population. Now, I said a couple of minutes ago that scientists are in the business of studying populations. You know, scientists are in the business of solving problems. How do they do this? They study populations. So, for instance, you know, an entomologist, you know, a person who studies bugs, insects, they're interested in the population of mosquitoes in St. Lucie County. A zoologist is interested in the population of zebras on the Serengeti in Africa. A clinical psychologist is interested in the population of depressed individuals, you know, in Broward County or whatever. Okay. Scientists study populations. My goal, actually, in measuring your heights was to determine the average height of the population of all IRSC students. Okay. Here's the thing, though. In most, if not all instances, whole populations, you know, like the population of the United States, are difficult to study because of time and money. So instead, we take samples from populations and study them. So you know what? I'm interested in the average height of all IRSC students, all 37,568 of you folks. But that would take a long time to measure all those heights, wouldn't it? Yep. So you know what I'm going to do? I'm going to measure your guys' heights. I'm going to measure your heights. There's 38 of you. And then make a generalization or an inference from sample to population. Here's where it gets good. Here's where the plot thickens. Ideally, and I like this word, you know, best case. You know, ideally, there would be no war. You know, ideally, everybody'd love each other, you know. Best case. Ideally, scientists take random samples, whereby each member of the population has an equal likelihood of being selected. A simple example. Let's suppose we're interested in the height of all IRSC students. So we write the names of all IRSC students on slips of paper and put them into a hat, mix them up. So we got a population, all IRSC students, 37,568. Let's say we have all these names on pieces of paper and we have them in this big bin and we randomize them. Okay, we whoosh them up. We can then randomly select however many names out of that bin. Let's say, you know, 1,000, or it could be, you know, 500 or 100 or even 38, you know, whatever. Now, just to back up a little bit, capital N symbolizes the number of observations in the population. Small n symbolizes the number of observations in the sample. And a sample is a subset of the population. Now here's the gist of what I'm trying to explain here. Because we've utilized randomization, because every member of this population had an equal likelihood of being selected, this sample is as representative of the population, theoretically anyway, as it can be. So any results that we glean from these 1,000 individuals can then be generalized through statistical inference back to the population from which the sample was selected. What do I mean by this? Well, let's suppose we take this random sample and we measure and we determine the average height is 5'6". We can now conclude that the average height of all IRSC students is also 5'6". Why, you might be thinking? Well, because every member of this population had an equal likelihood of being selected. This sample, you know, whether it be 1,000 or 500 or 250 or 100 or even 38, this random sample is as representative of the population, theoretically anyway, as it can be. So any results we get can be automatically generalized back to the population. So if this sample is indeed randomly selected, we can say, and we measure the average height to be 5'6", we can then conclude that, you know what? There's a pretty high likelihood that the average height of all IRSC students is also 5'6". Why? Well, because every member of this population had an equal likelihood of being selected, so this sample is as representative of the population as it can be. Let's continue. The ability to generalize. That's the goal here. That's what randomization does for us. You notice I have generalize capitalized. It's this big, important word. And so let's just go on. After measuring the 1,000 research subjects, we now have the ability to generalize those results back to the population from which we selected the sample. Now hold that thought and let's look at some more terminology. Variables. Oop, there's a mathy term, variables. We know what variables are, don't we? They're numbers that change. So all those height measurements, those are not constant. No, they're different. Student number 1 was 78 inches tall. Student number 2 was 63 inches tall. Student number 3 was, 71 inches tall, and so on and so forth. Variables are numbers that change. Now, there's a couple of types of variables in this course that we're going to be using throughout the whole course, okay? We have what we call the dependent variable, abbreviated using dv. This is the variable we measure. It's considered the outcome of interest, or just simply the data. So this list of heights is a dependent variable. It's the data. So any numbers that we're analyzing in statistics is indeed a dependent variable. Now we're going to be talking about experiments in a few minutes. Experiments in the scientific sense. We already know what experiments are. We do it all the time. But we're going to be learning what a scientific experiment really is. Now in the case of an experiment, the dependent variable is the effect in terms of cause and effect. Experiments provide evidence for cause and effect. So the dependent variable in the case of the experiment is the effect. The independent variable, on the other hand, we'll abbreviate it using IV, is the variable we manipulate to measure for its effect on the dependent variable. So the independent variable is considered the type of treatment. The independent variable is the type of treatment administered to measure for its effect on the dependent variable. So in a nutshell, this is the cause in the experimental sense, in cause and effect sense. This is the cause, this is the effect. The effects of the independent variable on the dependent variable. Okay, let's continue. Experimental research in many intro stat textbooks is covered in the first chapter. In our textbook, it's back in Appendix A. Take a look at it. And for the purposes of our class and our discussion, let's put some of this stuff together. We've been talking about, terms, statistical terminology, population, sample, randomization, dependent variable, independent variable, and generalization. Let's put this into a real-world example. Okay, let's see how this all works together. And this is an example of an experiment whereby, of course, we manipulate an independent variable, aka administer a treatment, right, and measure for its effect on the dependent variable. Let's look at how this works. And we're going to call this our headache pain study. Let's pretend we're a team of scientists and we have this pretty substantial National Science Foundation grant that requires us to study, to look at the effects of different headache pain treatments on the reduction of chronic headache pain. The effects of different headache pain treatments and their role in the reduction of chronic headache pain treatment. And we're actually going all around the world doing this, going to different headache pain clinics doing this. One of our stops is right down the road in Miami, Florida. Again, our study's aim is to test for the effects of different pain relievers on headache reduction. Now, just for the purposes of, from here on in, whenever you're in a scientific research article, whenever you're looking at it, here's the tip-off in terms of whether it's an experiment or not. Whenever you see the word effects in the title, that's an experiment. And it's the effects of the independent variable on the dependent variable. The effects of the independent variable on the dependent variable. Now, so we stop in Miami. And at this one particular headache pain clinic, there's actually 10,231 headache pain sufferers. But you know what? It would take a long time to study all these individuals. So you know what we're going to do? To make things a little bit easier and to make things like way more efficient, we're going to take a sample and study them. We're going to take a random sample. In fact, we'll have all the names, we'll have 10,231 names, and let's say on slips of paper. This is a simple example. They do it a little bit more sophisticated, Lee, but we'll just keep the example simple. Let's suppose we have all these names on those slips of paper. We randomize them. We whoosh them up in a barrel. We randomize them. We'll randomly select 500 names. Oop, Tommy Smith. Oop, Sally Jones. Oop. We have 500 names. That's our sample, our random sample. We then whoosh those 500 names up again and randomly assign them to 5 treatment groups. 5 groups of 100 to make our sample of 500. I'll show you the design in the next slide. The independent variable is always the type of treatment administered, the type of treatment. In this case, it's the pain reliever treatments, the variable we manipulate, the pain reliever treatments. The dependent variable, headache pain, that's what we're actually measuring. That's the actual data that we get. That is the outcome of interest. Now, headache pain cannot be measured conventionally. It's an intangible. So we can't measure it conventionally like we can pulse or blood pressure or other. So we have to create a scale. So we did that. The headache pain scale. 0 is no pain. 20 is extreme pain. Methodological stuff. The subjects were measured on headache pain upon admission to the study. Their overall mean was 15. A mean is it's an average. It's a measure of central tendency. And overall, their mean across the board was 15. Some of the subjects scored lower, of course, some scored higher. Their mean is 15. And the subjects in each group were then administered respective headache pain treatments, that's the independent variable, and measured after a 6-week period. And this is what the design looks like. And this is an example, a very simple example of a clinical trial. We actually have 5 groups of 100, as we see. This first group we call the control group. In any experiment, in every experiment, group number 1 is always the control group. What is a control group? Well, a control group is either the group that receives no treatment, or it's the group that receives some sort of traditional treatment. Regardless, the control group is compared to the experimental groups. And in this case, we have 4 experimental groups compared to the control group. And in this case, this particular group of 100 subjects receives a sugar pill. It's called a placebo. We have a pretest mean of 15. Pretest is that first measurement. The pretest, it's that baseline measurement. They're administered their respective treatments over the 6-week period as mentioned, and then they're measured again after the 6 weeks. This is called the post-test. We see reductions here, don't we? In fact, we see a 3-point reduction in the group that just got the, received the sugar. These folks actually believed that they were receiving medicine. They had a reduction in pain overall. That's the power of the mind. 5-point reduction here, 7-point reduction here, 8-point reduction here, 10-point reduction here. Because every member of that population class had an equal likelihood of being selected, we now have the ability to generalize from sample to population. What this means is that, you know what, you guys? What we're seeing here in terms of these reductions has a very high likelihood of also occurring in the population from which the sample was selected. Because each member of that population had an equal likelihood of being selected, this sample is as representative of the population as it can be. So any results that we get, in this case, these reductions, any results that we get, in this case, you know, these reductions, can be generalized back to the population. In other words, what we're seeing here has a high likelihood of also occurring in those 10,231, you know, research subjects that we have in our population. So, generalizability, there's that word again. We see significant decreases, mostly in Tylenol, ibuprofen, and naproxen. Because we've utilized random selection and random assignment, we may now generalize these sample results back to the population from which the sample was selected. Randomization and the value of randomization. Now, conclusions. We conclude that these effects may have a high likelihood of occurring in the population from which our sample was selected. The next step, well, let's take another sample. We're going to get on the plane and leave Miami and fly over to Houston. We're going to do an identical study there. Then we're going to go to Dallas. Then we'll go to Phoenix, and then San Diego, LA, San Francisco, Portland, Seattle, you know, and do the exact same thing. Gathering more data. The next step in the scientific method is always to get more data. It's called replication. And we're going to see if we have similar results. If we do, this is called converging evidence. In this case, for the effects of our different pain relievers on the reduction of chronic headache pain. Replication. So scientists replicate, get more data. Okay. Now, what we just did here, ladies and gentlemen, was an example of what we call a true experiment. It was a true experiment. Experimental research is deemed true experimental when it satisfies three things. And we satisfied those. The use of a control group, the manipulation of an independent variable, also called the administration of a treatment. The IV we know is the type of treatment. And the element of randomization, which we had in place there. Now, if you guys remember, I said ideally scientists utilize randomization. Unfortunately, most of the experimental research out there these days doesn't use randomization. They use volunteer samples, people that just walk in the door. Most of the experimental research out there these days, class, is what we call quasi-experimental. Quasi meaning similar to. Quasi means similar to. Most of the experimental research out there these days is quasi-experimental because of the lack of randomization in the selection of the sample. And these non-random samples are considered biased samples. Samples of volunteers, biased samples. And we need to take a look at the characteristics of biased samples. A biased sample is a sample in which some members of the population are less likely to be included than others. And the thing about biased samples is that there's no ability to generalize to any population. They're essentially, samples of volunteers. So for instance, let's suppose I did that height study with you 38 people, of course, with the goal of generalizing from sample to population. There's 38 of you individuals here. I measure your heights with the goal of generalizing that average to the population of 37,568 IRSC students. But let's suppose, half of this 38 class were the IRSC basketball team. Now remember, my goal is to determine the average height of the population. If I had, 16 or 18 or whatever, 19 IRSC basketball players in this class, these guys are uncharacteristically tall, right? Is that an accurate representation of the population of IRSC students? No. The average, the mean might be, of the class might be 6'1". Does that necessarily, can I generalize that? Can I say, the average height of all IRSC students is also 6'1"? No, no. We have a biased sample. Every member of the population did not have an equal likelihood of being selected. There are lots and lots of biased samples out there in our world of science and research, where people just kind of walk in the door and volunteer. Now, one of the dangers of quasi-experiments, well, let's just reiterate a little bit. In the quasi-experiment, we manipulate an independent variable, yep, and we use a control group, but it fails to use randomization. One of the dangers in a biased sample is the existence of what we call a confounding variable. And a confounding variable class is any variable highly related to the independent variable and or the dependent variable that may be affecting the accuracy of our results. Randomization actually reduces the risk. It reduces the potential effects of the confounding variable. It actually spreads the risk of the effects of that confounding variable equally across the groups. Let's take a look at just a quick example of this biased sample in terms of an experiment, and this is a quasi-experiment, okay? This is something very similar to the headache pain study, all right? Let's suppose I'm an educational researcher, and I'm getting ready to publish an article in the Journal of Educational Research, and it's called The Effects of Different Instructional Methods on Reading Achievement. And I actually have identified a population of all 6th graders in Port St. Lucie. All 6th graders in Port St. Lucie, okay? And I obtained a sample of 120 individuals, okay? And there's actually 3 groups. I have 3 groups of 40, 3 classes of 40. The independent variable is the type of instructional method, okay? The dependent variable is reading achievement. So I have our 3 groups, right? The first group is that control group. And then I have 2 experimental groups. The second group gets instructional method number 1. The first group is the control group. They get, just traditional instruction. The second group gets the, experimental, method number 1, some highly innovative, creative instructional method. And then the third group gets method number 2, some highly innovative, creative instructional method. And as it turns out, the mean for group 1 is 75, the mean for group 2 is 76, and the mean for group 3 is 96. Now, I forgot to tell you something. Number 1, in the selection of this sample, I didn't utilize randomization. You know what I did? I basically just walked into Port St. Lucie Middle School, and I walked into Mrs. Jones's class and measured them. Then I walked into Mrs. Smith's class, reading class, measured them. And then I walked into Mrs. Thomas's class, which is group 3. They got the really high score, remember? Well, you know what? Group 3 are the gifted students. I didn't tell you that. This is a biased sample. We have a potential confounding variable here. It's called IQ. IQ and reading achievement are highly related. So now the question becomes, is it the method number 2 that was administered to group 3 that caused that really, really high reading score? Or, was it just the fact that these kids all have IQs above 145? I mean, it stands to reason that these high IQ kids are going to read at a substantially higher level. Okay? And this is always a limitation of a quasi-experiment. Because we have groups of volunteers, there's always a pretty strong likelihood that we have some other variable associated with the IV or D fee that could be affecting the accuracy of our results. A better way of conducting this research is to get the names of all the 6th graders in Port St. Lucie on slips of paper, randomize them, randomly select 120 names, and then randomly assign them to 3 groups. If I were to have done that, that would have spread the risk of the existence of any of the IQ kids equally across the groups. Randomization creates, theoretically of course, equal groups on all variables. Randomization creates equal groups on all variables. So when we do administer the treatment, when we do manipulate that independent variable, we can pretty much detect real effects, real differences between groups. That only exists in the true experiment, though. Okay. We will get into statistical symbols in our next class. This will wrap up this lecture number 1 for introductory statistics. Have a nice day, and I will see you in our next class session.